morning. My name is Kathy Mtambanengwe. I'm a statistical consultant with Open Analytics. But this presentation is on a project that I'm working on for my PhD in collaboration with my promoters, Crystal Fars and Mark Arts from Hasselt University here in Belgium. So my title is A Restricted Composite Likelihood Approach to Modeling Gaussian Spatial Data. So I'll just give a brief background of the problem, and I'll show you how the methods work, some results from a simulation study, and the spatial record package that I made, and I'll show you some application to data. So likelihood methods are an instinctive choice when you're doing statistical modeling, but when you have complex dependencies like spatial data, then it's not always so straightforward because in most cases, sampling regions that are closer to each other tend to be more similar than regions that are further away. And with full likelihood, you usually have inversion of matrices in your likelihood, which gets computationally difficult when you have really large sample sizes. So composite likelihood is a method which breaks up the full information into smaller pieces and then makes computation easier, and then you combine them again at the end. So this is something that can be specified marginally or conditionally. And for most of my talk, I'll be considering the marginal case. So I'll just give you some notation to begin with. Imagine some observations Z at different locations S. So you have N observations, and they follow a normal distribution. So you have some mean mu and some variance parameters C. So you have a sigma and a rho, which are your parameters of interest. So mu is the mean, your variability or variance sigma squared, and the rho is the spatial dependence. So normally you can describe this by a semi-variogram function, which is just a function of the covariance parameters, and it just gives you an idea of how the variability in all your data is distributed. So I also focus mainly on the exponential case. So you have a variability at distance 0, in essence, this is your C naught, and then your variance, and then you have an exponential distribution. So if the phi parameter is an indication of the distances, of the correlation between the distances, your correlation is a function of the phi, and the larger your phi, then the smaller the correlation between the spatial points. So for maximum likelihood, you have an expression like this. So your covariance parameters are in the C matrix. So it's the size of the C matrix is directly dependent on the size of your spatial points. So this matrix can get really large if you have a large spatial region. And maximum likelihood is known to have some bias in the covariance parameters. So the maximum likelihood in itself underestimates the covariance parameters. So Harville in 1974 came up with the restricted maximum likelihood. So there's an extra penalty term, which is only a function of the covariance parameters. But like I said before, this requires full specification of your probability model and inversion of matrices, which is sometimes restrictive. Carriere and Lele in 1999 came up with the pairwise difference method. So you take a contrast of pairs between two different points and use this instead, a function of the pairs instead of the full function of your likelihood. And so essentially it's just a difference between the mean of each observation per spatial point. And so you have your covariance function and your differences, which are the main components of your model. But the problem with this is that the mean parameters are treated as a nuisance. So if you want to know the means in your regions, then with this method, you cannot get those details. And then Lessese and Van Houweling in 1994 came up with the pairwise marginal likelihood. So in essence, it's a function of different pairs of your observations. And in this case, since it's Gaussian, the pairs follow a bivariate normal. So you just do pairs, likelihoods between pairs, and your matrices are of the dimension of pairs, so it's 2 by 2 in most cases. And you just sum over all the pairs to get your likelihood function. And then now, in a similar way to the way restricted maximum likelihood corrects for maximum likelihood, we come up with a restricted composite likelihood method. So you have your pairwise likelihood in the first term, and then a penalty term, which is only a function of your covariance parameters, and you also sum between pairs. And we have an extra correction term, which is W star, which is derived from the effective sample size as defined by Fortin and Dale. So essentially, because you have correlated information, it's different from when you have fully independent observations. So essentially, suppose you have 100 observations. If they're really highly correlated, perhaps you have information only from, say, 30 points. It's as good as having 30 independent points rather than the 100 correlated points that you have. And this rho that's used in the calculation has to be estimated from the data. We have weighting for the likelihood. So since I mentioned before that regions that are further apart tend to be less correlated, so sometimes using information between these pairs does not give you any information because they're too far apart, so they don't add any information if you pair them. So you can choose subsets of all the pairs in your data. So, So say perhaps if it's unweighted, then all the weights for all the pairs is 1. You can use an inverse distance method, so pairs that are farther away get a different weight compared to when pairs are closer to each other. Or you can use neighboring information for the spatial regions to decide which pairs to use when constructing your pairwise likelihoods. And this can be defined in different ways, either sharing of borders or some maximum distance between the centroids of your spatial regions. For the standard error estimation, normally you can just use the Fisher information matrix, which is based on the Bayesian from your data. But since we're using composite likelihoods with independent pairs anyway, you can adjust using the Godard information matrix. So you have your Bayesian transposed, and you have the outer product of your score function and the Bayesian again, and this is like a sandwich estimator which usually corrects and gives you robust estimators. But the problem with this is your score function is dependent on the structure of your data, and the replications need to be independent or at least pseudo-independent for them to estimate it correctly. So for spatial data, normally you can try and use 2 different methods. So the first is the window subsampling. So you subsample over regions of your whole data, and then you calculate the score functions over the subregions and multiply by the size of the subregion and sum over all the subregions. And these regions can be overlapping or non-overlapping. And you need good mixing properties for this to work. Another option is to use Monte Carlo simulation. So you estimate your parameters, and based on your estimates theta, you simulate new data y and keep re-estimating the score functions, and then you get an average of your simulations. But yeah, this also assumes that the model you fitted is at least correct in some way. So we did a simulation study for our method. So the basic idea was we simulate data on a grid. So we chose different grid sizes. And then we vary mainly the variance parameter sigma and the dependence level with the rho, which is the correlation. So you simulate data with an exponential correlation with a pre-specified mean. And then based on the simulated data, you estimate the parameters using the different methods, maximum likelihood, restricted maximum likelihood, the differences method, the pairwise, this restricted composite likelihood with the true correlation parameter, and with the estimated parameter. And we repeat this 500 times for each grid type and dependence level specified. So these are some of the results. Because the penalty term does not contain any of the mean parameters here, you don't see any differences. This is the differences method, which does not estimate mean parameters, so there's no estimates there. But for the variance parameters, The number 2 is the restricted maximum likelihood, which is supposed to be closest to the truth. And our method does fairly well, especially when you have a weak correlation, so your estimates are much closer to the true values. When the correlation gets stronger, then sometimes it's a little bit off, but at least it's better than just using the standard pairwise likelihood method, which is number 4. This is for an 8x8 regular grid. We increase the grid size a little bit, and the estimates get better as you go. But it's more or less the same scenarios as before. And so just a summary from the simulation study, when you use weighting, you improve your estimates for the correlation parameters, and you have less bias. And if you don't know the true rho, then you can use the rho from the correlation from the differences method as an estimate for your effective sample size. We observe larger difference for stronger correlations, but this is not unexpected, because then indeed if your correlation is too strong, you have less information from all your spatial points. And variability reduces as you increase your sample size, which indicates some consistency. So for the package, currently it's only focusing on exponential correlation structure. So you input your data in geodata format. You can also input a shaped polygon. You have to specify a maximum distance which you want for your pairs. And for output, you get estimates of the mean and variance parameters. If you use subsampling as your variance type, then you get the subsampling regions which you can plot. And you also get the neighborhood and pairing information that was used for the method. So the package is still in development, but will be made available on this website. So some real data. This is wheat yield data. You have a 20 by 25 lattice of plots, and the response was wheat yield, which is Gaussian. So you can see how some regions in this area tend to have lower values. In here you have high values, so we expect some correlation there. And these are the results from different methods. So I show maximum likelihood, restricted maximum likelihood, pairwise likelihood, and the restricted composite likelihood. And for the mean parameters, there's not much difference there. But for the variance parameters, then you can see the pairwise likelihood really underestimates the variance here by itself, and the restricted composite likelihood corrects for that. Here you don't see any standard errors because the function I used does not return standard errors for the covariance parameters. This is a different data. It's on thyroid stimulating hormones in newborns in Galicia, Spain. And the covariate is the mean birth weight, and the response is the TSH levels. And these are your spatial points on a spatial polygon, I should say. And these are your results. For this case, the correlations were really small, so you don't see anything there. But for your variance, you see that the maximum likelihood and pairwise maximum likelihood are really similar, and the restricted maximum likelihood and the restricted composite likelihood tend to be similar as well. So in conclusion, it seems penalization is important when you're using a pairwise composite likelihood method and you have interest in your covariance parameters, and you have less computation time. I tried it with 10,000 points on a spatial grid, and full restricted maximum likelihood took about 5 hours, and my method on a subset of the data took about 15 minutes, so it's a huge gain in time. And yeah, you improve estimates of covariance parameters, and it's also important to consider how you estimate your standard errors depending on the type of data you have. And I included some references, and thank you.
We have a few minutes for questions. Yes, please. Is cross-validation estimation of the parameters kind of out of style, or is it just not competing? I noticed you haven't considered it.
To be honest, I didn't consider it, but yeah, it's an option. Yeah.
More questions? Maybe I have one case. Do we have any results from the simulation study on coverage?
Yeah, I did have some information, but I didn't include it here. But I'm working on the paper now, and I'll definitely include that.
Okay, that would be
It would be interesting as well.